For a drag force, it's proportional to velocity squared. Often objects moving fast through air is the case for this. There's an equation given in the book that you're going to use once or twice on your homework, but your homework is the only, just so you know, the homework is the only place that you're going to use this particular equation. Just so you know, if you do this on a test or an AP exam or whatever, it'll just say something like the resistance is minus something times v squared. That's all it'll give you. Okay, so D is something called the drag coefficient. Rho is the density of the air, not the object. A is the cross-sectional area. Meaning what area is hitting the air, and V is the velocity of the object. So for Newton's second law, in this case, we've got, again, net force equals m dV by dt. All right. In this case, if we have an object falling through the air, we would have mg minus 1/2 d rho a v squared equals m dV dt. Although again, like I said, on the AP exam or something, it would probably just be bv squared or kv squared or something like that. Find the terminal velocity. Again, that's just where our acceleration is 0. So then we just do algebra to get that the terminal velocity is 2mg over d rho a square rooted. Right? And then write the differential equation you would need to solve in order to find the velocity as a function of time. Well, this is the equation, and what this is asking you to do is rearrange it. So we would use kind of the same method we did on the other one. Separate the variables and go whoop. And this is the equation you would need to solve. This actually isn't nicely integratable. I don't know what the word is there. What can happen with a velocity squared resistive force is something like this. Like at the end of an amusement park ride, roller coaster cars of mass number traveling at speed v initial. The coaster applies a net resistive force that is proportional to the square velocity until the car comes to a stop. With constant of proportionality k, find the velocity of the cars as a function of time. So in this case, all the net force that we have is just this resistive force. And in this case, you could solve the integral because we just have a v squared. So we can move all of our not v stuff to the left side, move our v stuff to the other side, integrate from v initial to v, from 0 to t, we have minus kt over m. And over here, the integral of 1 over v squared is minus 1 over v. So we have minus 1 over v, and we're evaluating that from v to v initial, so we plug in v, plug in v initial, subtract v initial to the other side. Well, actually add this over, so then we have 1 over v would be equal to 1 over v initial plus kt over m, so then v would be the reciprocal. And you could do things with denominators to make that look a little bit nicer, I guess. You can multiply by mv initial over mv initial. So then we get v equals mv initial over, what would this be, m plus k t v initial. And that would be your velocity as a function of time.